cell. This is a single unit cell. Passing through these different axes will be passed through the centers, and all the axes are not having in a same length and the same direction. Different axes are having the different lengths according to that which is classified. And then not only that one, in a particular angle, the crystal it should be rotated once. And again, it is divided into the parts. So here, example for if you see the uh, symmetrical symbol, maybe if it is a 1, yesterday I told you, the axis of symmetry, 1, 2, 3, 4, or 6. So, according to that, the these axes once it will be rotated that from the center point we will get the faces. Sometimes the faces it is equal, so that is known as a monoid symmetry, single face or one fold, or sometimes maybe it is a dyad. Dyad means two-fold axis. Two folds will be there. This is practically in your practical class. You will get knowledge about that. Uh, Suppose just this, you can imagine whatever it is that I am saying with that. You can imagine the crystal. You can imagine this is the center point of that one, and you see through this is the center point. One axis will be go. So now once you can rotate uh, based on this, once if you rotate, how many faces it is showing? Similar faces or different faces it is showing. So according to that, we will give the name of the axis symmetry. So the same faces, it will become, it is known as a monogonal. Or sometimes what is happening, different faces will come. Once if you are rotating, different faces will come. Once it, uh, one time it will become, another side it will become. This will come. So that this is known as a two-fold of a symmetry. The angle it is 180 degrees. Angle inclination it is 180 degrees. 180 degrees. So that it is known as a dyad and a two-fold symmetry. And third, the angle maybe if it is a 120 degrees of angle, the inclination, and here threefold, threefold. Now, suppose if it is 120 degrees of angle, 120 degrees of angle, it is a straight 90 degrees. It's 90 degrees almost. And then maybe sometimes we see it is in a 120 degrees. I'll show you on goniometer. Let's say what we have seen that goniometer. I'll show you once again. Yeah. Here in this goniometer, I hope you have seen this one. In this goniometer, just you can see the angle maybe if it is in a crystal angle in a crystal axis, the axis it will be passing through this one, through this one. Suppose if it is a passing through 90 degrees, and so it is passing through this one, so that the you see it is a simply and logic, simple thing. 120 actually the rotation it has 360 degrees. So so the from this is the center point. If it has a similar phases, the axis passing only one through this one, through the center point. So it is a angle 360 degrees. It is known as a monopolar. Suppose you can divide into the two parts of this one, 180. So automatically the crystal it is dividing into the two parts. So that 360 by 2, 180 degrees. So it is known as a diagonal. And again, in the same 360 degrees of angle and the axis of we what we see, it is rotating three times on 120 angle based. So that it is a trigonal. It is known as a trigonal. And 90 degrees, exactly, this is the 90 degrees of the crystal system. It is divided into the four parts. This is the one. Yeah, wait. Yeah. This is the one, two. So one, two, three, four. Four parts, it's a dividing into the 360 degrees. So it is known as a tetragonal. And sometimes we can see it is the angle at a 60 degrees. It is known as a hexad, six-fold symmetry. The axis it is known as a six-fold symmetry. It is called as a hexagonal. It is called as a hexagonal. So based on this name of the symmetrical elements, the folds will be created and the folds will be defined. According to that, we will classify. Now coming to that, the classification. So here there are seven types of universal classifications are there. One, it is cubic. Second one, it is tetragonal. Third one is orthorhombic. Fourth one is a monoclinic system. Third one is hexagonal. So fifth one is hexagonal. Sixth one is a trigonal. And seventh one, it is a triclinic here. Triclinic system. Yeah. These are the classification of crystals which are useful for to identify the mineral, and every mineral it has a own crystal system. Here you see the first one, it is isometric or cubic system. The first one it is called as a this one, the cubic, or it is known as a isometric system. So here how we can divide that. The length of a crystallographic axis, it is a depend on their axial ratios, and it's a depend on their angles. Angles which are cut down into the R, which are angles are uh, formed by the passes of passing of axes corners, through the corners. So here different crystals are having the different shapes based on their unit cells. So again here, seven crystal systems which are divided into the 32 classes. 32 classes. In 1930, Hessel was a familiar crystallographer and he predicted that number of classes. Okay, now till I mean, from that onwards till the same classification will be followed. Almost all commonly we see the 15 uh, classes. Almost all we will up will start there. Yeah, so that here commonly will occurring almost 15 classes. The from the above mentioned like 32 classes. Particularly, we will see the seven crystal systems. From these seven crystal systems, commonly we will identify the 15 classes, how they are arranged, and how they are established on the basis of a number and position relative axis length, as well as axial ratios also, and axial angles, and how they are formed. We see that. Okay, in a normal class, we see that is a holohedral or a holosymmetric crystal system, which is exhibiting the highest degree of symmetry or highest degree of symmetrical elements among these seven crystal systems. Normally, we see this one. Okay, don't worry. You okay? Now we see that this is this picture. What it is showing here. You see this one. It is a unit cell, and it is noticing that the different axes are there. Different axes that are there. Crystallographic axis, you see axis A, axis B, and axis 3. C. So here the inclination of angles which are represented alpha, beta, and gamma. Between these axes, you see here alpha, beta, and gamma. How do we classify these crystal systems? Depend on their number of crystallographic axes and Sorry, I'm getting a little bit network problem here. So for the interruption, again we'll come back. Yeah, cubic system or isometric system. These crystals almost all are the axes are equal and which are having the equal length also. Equal length also. Just you see here, this is uh, first picture A isometric or cubic. You see here, you see here. Each one angle it is. See here, A1, A2, and A3. A1, A2, A3, and each one angle or each one axis which are intersecting to each other at 90 degrees. 90 degrees. So here the alpha is equal to beta is equal to gamma is equal to 90 degrees. Or if you feel this is A axis and the B axis, C axis is equal to 90 degrees. So equal lengths which are having these lengths means the axis lengths are in a equal. So that is the reason we will show that is as A is equal to B is equal to C and almost all these are intersecting the same angle, that's 90 degrees. So that alpha is equal, beta is equal, gamma is equal to 90 degrees. So in all sides, these are all the equal in back and the front also. So we will call it is a isometric equal. Iso means equal, equal isometric system or cubic system. We'll call it is a cubic system. And second one, it is this one, the tetragonal. This is a tetragonal. Here, almost two out of three crystallographic axes. You see the suppose example the C axis you can see here. C axis. You feel maybe that it is a B, and C. So this A and B are A1 or A2. These two are having equal length. But whereas the C, it is not equal to this two. So that we will call that is A is equal to B naught is equal to C. You see here, this is, it is mentioned here. It is mentioned. This one. Okay. Two horizontal axes of equal length. These two are having equal length horizontal, but the vertical axis, it is not equal to these two horizontal lines or horizontal axis. So A is equal to A and B is equal to A here, and the alpha, beta, gamma is equal to 90 degrees. But anyway, the angle, it is intersecting in 90 degrees only, but the length, it is different. So that the axis length ABC, it is known as the axis length, and alpha, beta, gamma, it is inclination, the angle inclined in the center point of the crystal. So there it will be shown as a alpha, beta, gamma is equal to 90 degrees because of these three axes are uh, internally intersecting at 90 degrees. So that is one reason. And here given some examples for this. Yeah, for these crystal systems. So here the past isometric system or in a cubic system, the best example for this one here, the galena one mineral and fluorite, rock salt, garnets, and some other examples of the crystals that are the important. In a tetragonal system here, the best example for this one, zircon, rutile, and scapolite. The zircon, it is very important, and rutile, it is also. These two are the very important, and which are commonly we see in a igneous terrain or in igneous rocks. So there, these are the two having the tetragonal system. And third one, it is a orthorhombic system. Here also almost all the crystallographic axes are having the different length almost. See, these three are having the different lengths. A, B, C. These three are having the different lengths. A, it is not equal to B. B is not equal to C. So we see here the length A, it having the short length, and B little bit it has the uh, middle length, and C vertical, it has a highest length compared with these two. So the according to this lengthwise, those are not equal. So that is a reason we will show that is A not it is equal to B not is equal to C. But whereas you see in a inclination of angle, that is it's a reference represents to the alpha, beta, and gamma. Alpha is equal, beta is equal to, gamma is equal to 90 degrees. This one 90 degrees. So that A even though A naught is equal to B naught is equal to C, but here axis wise, inclination wise, these are intersecting the maintaining of a 90 degrees of angle. So that is the reason alpha is equal to beta is equal to gamma is equal to 90 degrees angle it is mentioning. So what it is the example for this one? Yeah, here the best example for this one, Barite. After that, there are some families also there based on this one. Barite family, Zircon family, Galena family, like that. Some of minerals are included in this group. Based on that, it is classified again. So in the orthorhombic system, you keep in your mind all the axes are intersecting in 90 degrees. So that is will show it is in a 90 degrees. Alpha is equal to beta is equal to gamma is equal to 90 degrees. But the lengths are different here. A axis, B axis, and C axis are not having the equal lengths. But whereas you can see in second one, in a tetragonal system, only two lengths are equal. A is equal to B, B naught is equal to C. In a isometric system, A is equal to B is equal to C. And in three groups also, or in three classifications also, almost these are all having the intersecting angle 90 degrees. So that is one thing. And next one, it is a monoclinic system here. In a monoclinic system, almost all the crystallographic systems same. What we have seen in a previous, all the crystallographic axes are having a different lengths. And here, the B axis is lies normal to the C and A axes. So that here the B axis maybe sometimes it is less than or others. Less than others means here less than maybe it is an 90 degrees. 90 degrees. So that less than beta it is less than 90 degrees, and alpha and beta, this alpha and beta, sorry, alpha and gamma, these two are having the 90 degrees. So here slightly the variation we will, you observe the variation here. You observe the variation. So that only two angles are intersecting in a 90 degrees. That is alpha and gamma. But beta it is not intersecting at 90 degrees. It is less than 90 degrees. It is showing the less than 90 degrees. So that keep in your mind, this is important thing here. And your next one, it is your triclinic system. Almost here all the crystallographic axes also having a different length, and the yeah yeah triclinic, yeah, the inclination of angles also which are having almost in a different cases. So that alpha it is called beta is equal not is equal to gamma not is equal to 90 degrees. Maybe it is having the high, or sometimes maybe it has a less, depend on their depend on their formation of axis. So that here confirm it is confirmed that all the crystallographic classes axes are having the different length. That's one. And second one it is that yeah second one it is that the same axis of intersecting of angle also not the same. It is not equivalent to the 90 degrees. Maybe it is a less than or greater than 90 degrees. 90 degrees. So it is known that alpha not is equal to beta, not is equal to gamma, and not is equal to 90 degrees. Not is equal to 90 degrees. The next one it is hexagonal system, hexagonal system, and here what it is the example for this one. In a triclinic system, almost we see the axonite type of minerals and the plagioclase type of minerals, and kyanite, albite, rhodonite. These minerals will be there. These are the classified into this group or joined in this group. And next one is hexagonal system. We see that in a hexagonal system, it has four crystallographic axes almost in the horizontal plane, and one it is one only one it is having the equal length. Only one it is having the equal length in a hexagonal system. You see here that uh, whatever horizontal planes of axes, these are having the equal length A1, A2, and A3. These three horizontal axes are having the equal length, except the vertical. See, it is indicating here. The C it is indicating here, it is vertical, but it is not equal to length of this one. So that A1 is equal to A2 is equal to A3, and these are intersecting at 120 degrees here. 120 degrees. It is perpendicular to the C. It is perpendicular to the C. So almost here, the C axis, the length of the C axis is having the high. It has a high length and compare with the remaining three. So we'll call simply A1 is equal to A2 is equal to A3, not is equal to C also. And A1 is equal to A2 is equal to A3 is equal to 120 degrees, and but C it is not. So this is about hexagonal. What is the example for this one? Here, beryl type of minerals. Beryl is the best example for this one. And your triclinic, and one more thing, it is that trigonal system. In a trigonal system, you see here in a trigonal system, almost all it is also having the four axes. It's also having the four axes A1, A2, A3. These four axes, see here. Yes, it's also having the four axes. It is similar to that hexagonal because of the horizontal plane of axes are equal, but they are intersecting at 60 degrees and 120 degrees. They are intersecting at 60 degrees, 120 degrees. You see here it is 60 degrees, and see it is intersecting with others 120 degrees. So A1, A2, A3 is equal to 60 degrees, and C it is indicating as a 120 degrees. The best example for this one, calcite. The best example for this trigonal system, um, it is a calcite, and hematite also these two, and corundum it is also will classify into the same. Here given one table, you simply it is very easy to understand crystallographic axes and the angles as well as the classes here. So here the crystallographic axis and axial angles of seven crystal systems. You see in a seven crystal system, just you can check out how many are there into classify into that. 5 plus 7 plus 3 plus 3 plus 7 plus 5 plus 2. These two. Totally 32 classes. Again, it is each system it is divided into the 32. Each system into divided into depend on their availability of access and angle axial angles, it is divided into the different classes. Yes. The cubic system or isometric system, it is divided into the five classes. The general appearance of a crystals, just you can see here on the table. The first column, it is a serial number of crystal system. Second one is a crystal system. Third one, general appearance of crystal, and photographic axis and axial angle. This will be there. Yeah, this is the table which is providing the information of crystals, general appearance of the crystals, and crystallographic axis also, axial axis, and then classes. That's one, it is a cubic system or isometric system. It is general appearance. We will see it is a equidimensional. Equi- and, uh, told you that is A is equal to B is equal to C. These axes are all having the equal length, so that the axial angle, it is dividing, it is intersecting at 90 degrees only. So that alpha is equal to beta is equal to gamma is equal to 90 degrees, and five classes. Let's see what are the five classes. Yes, one, it is a tetragonal system. Long crystals are squarish cross section of crystals we may see in here, and A is equal to B and B naught is equal to C. Almost that means here one C of axis, it has a length, may length compare with two other axes like A and B. And axial angles are A is equal to, alpha is equal to beta is equal to gamma is equal to 90 degrees. That means here, similarly, like a previous cubic system or isometric system, it's also having intersecting at 90 degrees only. So that here again we will show angles is equal to beta is equal to gamma is equal to 90 degrees, and it is divided into the seven classes. Third one, it is orthorhombic system, the brick-like and stubby or short prismatic structure, which are equal different lengths of axis will be found. So that A not equal to B not equal to C, and A is and lengths are different, but The inclination, or maybe it is a intersecting of an angle to each axis. It has a 90. And it is called beta is equal to gamma is equal to 90 degrees. It is classified to the three types. And fourth one, it is a monochrome, same. Here it's also having the same appearance. Crystallographic axis are A naught is equal to B is equal to C. But whereas only one angle B, it is beta, it is less than 90 degrees, and it is not equal into the 90 degrees. So that A is alpha it is equal, gamma is equal to 90 degrees, and it is classified into the three classes. Yeah, next one, in a hexagonal system, it's a columnar and a shorter long prismatic structure which are having. And here we can see the four axes, but all are not equal. Three horizontal axes are equal. Those may be A1 is equal to A2 is equal to A3, not is equal to C. C, it has a vertical vertical line or a vertical axis. Here alpha is equal, beta is equal to 90 degrees, and whereas the gamma it is equal to 120 degrees. The C axis it is intersecting here. C axis it is intersecting here at 120 degrees. 120 degrees, and it is a classifying as a seven classes. And sixth one is a trigonal system. It has a columnar, short or long prismatic. Similarly, it is also like a previous. All the angles are not equal, and all the axes are also not equal. Only two axes are intersecting at 90 degrees. Alpha is equal to beta is equal to 90 degrees, and which is classified into the five classes. And triclinic, it's the absence of right edges and the places of edges. It's not having the equivalence, and intersecting it is also not equal at angle. So A naught is equal to B naught is equal to C, and alpha naught is equal to beta naught is equal to gamma naught is equal to 90 degrees. It is classified into the two classes. So coming into the detailed study of each system. The first one, it is a cubic system. The cubic system, it is also known as a isometric system, and the crystals almost it is belongs to the isometric means here equal length or equal. Iso means that equal, and metric means measuring. So here three crystallographic axes are passing through the center point and through the corners and intersecting the equal lengths, and which are having the equal length also. Length. So um, you see in this picture A or A1, A2, A3. The A1 it is moving its front to the back. A1 it is moving to the front to the back, and A2 it is moving from right to the left, and A3 it is moving from top to bottom. This is top to the bottom is A3. So these are the three axes. These are the three axes are there. The angles also you see each one, these two horizontal angles, or it is a diagonal, you may call it is a diagonal A1 front to back. The backside, whatever are passing into the backside, will give the negative numbers. I mean negative indices. Minus A1, minus A2, and minus A3. The front side, it is moving from front to back. It is uh, positive index. Positive index. The sign it is showing as a plus uh, A plus A, or A1 also we'll call. So the angle you can see here almost all 90 degrees. I told you just now. All are in a equal angles and equal lengths also. The axial ratios, it's equal ratios, so that 1:1:1 we will show that. In the first picture, you see here the lines how they are arranged. It's moving from this side to this side. and this is from this side to this side, and diagonal from this which are moving. So according to that, we will see. Just this one. It is a galena crystal. It is known as the galena crystal, the model of a galena crystal. So that is, we will call this is known as a galena type of, yeah, galena type of a crystal system also. So observe carefully. These are all the imagine lines only. Imagine lines only. Imagine lines only. And these galena type of a system, it has five symmetry classes. We will call it is as a normal crystal system also, and normal cubic system. Normal cubic system, we will call that is a normal cubic system. So yeah, symmetry elements here. The symmetry elements in a cubic system, it has a highest degree of symmetry system. It has a nine planes. It has a nine planes, and 13 axes are there. Nine planes and 13 axes are there. You see, the planes means this one. These plane surfaces, whatever we are observing. These three are the diagonal planes. So three are the axial planes according to the axis. Three are the axial planes, and six are the diagonal planes. Yes, and diagonal planes. This one. Just you can imagine this one. And axis also. Here, normal three crystallographic axis. Yeah. Normal crystallographic axis, three normal crystallographic axis, and four opposite solid angles, and uh, six midpoint and opposite edges. Six. Just these are all the imagine. You can imagine these are all the normal classification of a cubic system. Nine plane symmetries. There's a nine plane symmetry. Three axial planes. Axial planes means the axis how they are traveling through these planes. This one, and this one. Three. So just you can imagine this front is diagonally, and this corner based. Front side, back side, and side. So these imagine lines, we can imagine it. Yeah. Here, suppose if you are taking the one cube, now you are rotating into the 90 degrees in a perpendicular to the any pair of axes, any pair of that. So here we will get the twofold axis. We will get a twofold axis or single fold axis. Almost we see here in a single fold axis we will get one fold axis because of almost all planes are equal here. So that we see here single fold monogonal formation. If you are holding, this is opposite direction, opposite direction. This one and this one, you see, there is a differentiation from this to here, and from this to in mid of that, in mid of the cube, you see. Along the three axes or along the three axes, you can rotate it. You will get a single, you will get in a first phase, in this phase we will get monogonal, and in the second phase you will get threefold, and through this one you will get a fourfold symmetry. Because of opposite direction, inclusion of opposite direction, inclusion of opposite direction, we'll get folds, different folds. So now coming into the forms in this one. Here you see the forms. The first one, it is a cube structure here. The cube structure, it is a solid bounded by the six faces. Yes, we know that it has six faces. One, two, three, and the other sides also three. The other sides of also having a three. The other sides of three, we see. The other sides of a three, 3 plus 3. In a cubic system, you keep in your mind here the forms or classes. One, it is a cube, it has a six faces. Each face again it is a cutting the one crystallographic axis. One crystallographic axis in each face. For example, per you see the top face and it is cutting the one crystallographic axis. So the remaining two it will be not cutting. Remaining two faces it will be not cutting. So that is the reason it is showing 0, 0, 1. And in a horizontal V, and it's showing 1. But uh, the second one here, it is a cutting the 2. So that it is a 101. Because of the other face will be added here. So that is the reason it will be cutting the two faces. Yes. Next one, it is a rhomboidodecahedron. Rhomboidodecahedron. It has 12 faces, bounded by it has 12 faces. In previous one, in a cube, it has 6 faces. This is a rhomboidodecahedron. In practically, if you see, you will get good idea and good experience. Octahedron. Next one, it is a octahedron. In a octahedron, this one, it has 8 faces. The top one 4 and the bottom one 4. Bottom one 4. This 4 and this 4. Octahedron. And the trapezohedron with the face symbols. This one, you see, trapezohedron. It has 24 faces. 24 faces. See, 12 will look 12 front side, and 12 it will be reflecting into the back side. It will be reflecting into the back side. Just you see here, it is a rhomboidodecahedron. Rhomboidodecahedron. It has 12 faces. And octahedron, octa means eight faces. And the trapezohedron, it has 24 faces from this side, front side, it has 12, and back side it has a 12. So this is the classification of uh, cubic system and tetragonal system. In a tetragonal system, you see here the crystallographic axis. There are three crystallographic axes, which we can see it is a right angle perpendicular to each other. Same. Two horizontal axes are equal, but third one it is not equal. It is vertical and it has a little bit length compared with the two. Okay, we compare with the two. So that here the axis one, I mean A or A1, whatever maybe you call it, is run from front to back. This you see here, front to back, and the B it will be run from uh, right to the left, and C it is a vertical. It has a different length compared with this two. You see here it is a mentioned one and one, but it has a shorter length compared with this two, 0.9. The symmetrical elements and the first thing, one more thing it is, we will call normally zircon type of crystal system. Because of the zircon, it is the best example for this one here, and the zircon type of a crystal system. In the number of symmetry elements, five, here we have a five planes and the three axial planes, planes. Yeah, the symmetry elements, five planes it has, and axes are five here. See, five planes, three are axial planes commonly, and two are the diagonal. One it is in horizontal, and second one it is a vertical plane. The axes are three crystallographic axes, and four on vertical face and edge. Here, center of a symmetry it is also present. Only one. You see the model here. It is a wooden type of crystal holding in a position. Top and the bottom cones you can hold it, and you can rotate that one. You rotate it 360 degrees. You'll find the three axes and four symmetrical folds and four symmetrical folds. We'll get it. And sometimes you can hold along the vertical and horizontal, these two. The faces you can see four. Suppose if your vertical faces, if you find out that, and you will get that is four axes and two fold symmetry. So this is the important of this feature and forms. Here the pinacoid type of forms are there. Pinacoid type of forms. Just wait. Okay. Yeah. Here pinacoid type of forms we see. Basal pinacoid, which is open forms to the rectangular faces, two rectangular faces, this and this side and this side and this side and this side. Each face is cut into the vertical axis and remain two are parallel. It is a vertical face. It will be cutting, and these two remaining are parallel to each other. So these two are horizontal. This one horizontal. This one also horizontal. And the tetragonal prism of second order, and it is also often formed for four rectangular faces. Four rectangular faces it has, and it will be cutting the four axes also, two horizontal and two are the vertical. Okay, here hexagonal system and the crystallographic axis are you see here are it is A1, A2, and A3. Only two are having the but equivalent, and the third one it is not equal to that. You see here it is look like it's a barrel type of a crystal system we call. Here the planes are seven planes as we find seven planes of a several axis, one horizontal plane and six vertical. And from this is a vertical, three is axial and three is a diagonal. So practically, if you can see, you will get a good understanding. Okay, but only these are all the imagined lines what I'm showing. Okay, we'll discuss continue in the next class the remaining formations of remembering crystal systems, and the next class will start the mineralogy also, because of we have more three classes for that, and there are different groups are there in the mineralogy, silicate groups, non-silicate groups, and silicate structures. Those will be also will study. Okay, we'll see in the next class. Thank you.
No, thank you. I created the group, sir.
Sorry.
I created the group, sir. I created the group. Can you share the material?
Okay, okay.
No, thank
Yeah,
you.
I'll send you.